So last time we defined analytic functions, and the definition I will repeat again. So this S was open set. So S was open, and then this is complex valued function defined on open set, and F is said to be analytic. In S if F is differentiable at every point of S. And naturally, therefore, if F is analytic in S, then throughout S, the real and imaginary parts of F satisfy Cauchy-Riemann equations. So we have seen that function can be written as uxy plus I times vxy. And what is relation between differentiability of F and differentiability of u and v? What is relation? Relation is that F is differentiable if and only if u and v are differentiable and satisfy Cauchy-Riemann equations. So analytic means this will happen throughout the open set S. So throughout S, u and v are differentiable functions, and further they satisfy Cauchy-Riemann equations. Okay. So that is what analyticity means. And later on we will see that this in particular would imply that F dash is differentiable. That means not only u and v are differentiable, the first order partial derivatives of u and v will be continuous, and not only that, the second order partial derivatives will be also continuous, and so on. So once it is analytic in a domain, we will see that F dash will exist, F dash will be differentiable, so F double dash will exist, and then by the same reason derivatives of all orders of F would exist on S. That will come later. At present we just want to see what are implications of analyticity. Alright. So differentiable and analytic, the difference is that differentiability is at a point, whereas analyticity is typically on an open set. Even when we say that analytic at a point, then that means there exists a neighborhood of that point throughout which the function is differentiable. So that also, let me repeat again. So when a terminology like this occurs, that is F is differentiable, F is analytic at Z0. Now here we have defined analytic function on open set, but what do we mean by this then, analytic at Z0? If there exists delta such that F is differentiable or now here you may say analytic in delta Z0. So throughout the neighborhood of that point, so if this is Z0, then throughout the neighborhood of that point, and then neighborhood is an open set. So on this open set, the function is differentiable at every point, or on this neighborhood function is analytic. That is what we mean by analytic at a point Z0. It may happen, last time we saw examples, that function is differentiable at a point, say Z0, but it is differentiable only at that point. So no matter which neighborhood you take around Z0, there are points in that neighborhood where the function is not differentiable. That means you cannot find such delta, where in that delta neighborhood function will be differentiable everywhere. So if no such delta exists, but it may happen that only at point Z0 function is differentiable. In that case, we just say that it is differentiable, but it is not analytic at that point. For analyticity, we need a neighborhood, okay, like that. So that is difference between differentiable at point and analytic at a point. Okay. All right. So Then we saw some examples last time of analytic functions, and today we'll move ahead and do some more examples of analytic functions and some implications of analytic functions. All right. So maybe you have the notes that I gave you last time, and let us see that. Okay, so let us see this example that Fz. So let's do this. Fz equal to 2xy plus I times x square plus y square. Two xy plus I times x square plus y square. So what is uxy? What is uxy? So here uxy is equal to uxy is equal to 2xy and vxy is equal to x square plus y square. So what is dA by u by dA by x? It is 2y. I think we did this example, but let's revise again. DA by v by dA by x is equal to 2x. DA by u by dA by y is 2x, and dA by v by dA by y is 2y. So we want dA by u by dA by x equal to dA by v by dA by y. So this is all right, but then we want dA by v by dA by x is equal to dA by minus dA by u by dA by y. Okay. Yeah, we did some other example last time. So this, let's see what happens here. So at points where the Cauchy-Riemann equations are not satisfied, the function cannot be differentiable at that point. So first, let us eliminate points where Cauchy-Riemann equations are not satisfied. So at which points they will not be satisfied? So we have to have dA by u by dA by x equal to dA by v by dA by y. That is satisfied everywhere. Okay. So dA by u by dA by x is equal to dA by v by dA by y. No problem. Now we want dA by u by dA by y equal to minus dA by v by dA by x. So this in turn implies now dA by u by dA by x is dA by u by dA by y is 2x equal to minus 2x, because this is also 2x and this is 2x. So this implies x equal to 0. 2x equal to minus 2x, then x equal to 0. So there is no restriction on y. So, but then x must be 0. So if x is not equal to 0, okay, then Cauchy-Riemann equations are not satisfied. Not satisfied at what? X comma y. So for all points x comma y where x is not equal to 0, Cauchy-Riemann equations are not satisfied. They are satisfied at 0 y, and Cauchy-Riemann equations hold at 0 comma y. And further, these first order partial derivatives being polynomials, they are continuous. Okay? and the function u and v in fact are differentiable everywhere. So at points where Cauchy-Riemann equations are satisfied, the function f will be differentiable. Okay. So at all points z equal to 0 plus I times y, that is z equal to iy, points of this type, fz is differentiable. Perhaps you will be able to see this example. Okay, let me find out the example in the notes that I have given to you. Yeah, it is there on your screen now. It is there on your screen. That is this example that I am talking about. So discuss the analyticity of the function that I have written here, 2xy psi times. So f is differentiable at all points of the type iy. Now let us see where these points are. Iy means the real part is 0, that is x is 0, so that is y axis. So at all these points on y axis, at all these points exactly on y axis, function is differentiable. So f is differentiable at all these points. Okay. What are points of analyticity? Where is it analytic? So at other points like this point or this point, there is no question of checking analyticity because it is not even differentiable, because Cauchy-Riemann equations are not satisfied at other points. If x is not equal to 0, x is equal to 0, that means only y axis. So Cauchy-Riemann equations are satisfied only on y axis. Therefore those are points which we need to check whether the function is actually analytic at those points or not. Now see, if you take any point on y axis and find a neighborhood, then that neighborhood cannot completely lie inside y axis. That means there will be at least one point outside that. The y axis is not an open set. Okay. So in fact, even if you take any point, you will not be able to find a neighborhood. So for any z0 of the type I times y, for any z0 of the type I times y, f is differentiable but not analytic. Differentiable but not analytic. Because we cannot find delta that does not exist for any such point. In fact, for any such point that does not exist, delta positive such that f is analytic in n delta z0. That means it is not analytic at that point, because it is still written here that f is analytic at z0 means what? F is analytic at z0 means there should be a neighborhood such that f is differentiable throughout the neighborhood. So this function is differentiable at infinitely many points. In fact, differentiable at all points of y-axis. It is differentiable everywhere, but differentiable everywhere on y-axis, but not analytic at any point. So in fact, this is differentiable at infinitely many points, but analytic nowhere. So the function is nowhere analytic. Is nowhere analytic. Now next problem, that is problem number 6. So do you see problem number 6? Show that fz is analytic in a domain D if and only if f bar of z bar, that is f of z bar is analytic in D. Okay. So let's try to solve this problem. These problems give us chance to use Cauchy-Riemann equations and apply the equations again and again, verify them, and get used to the fact that a differentiable function satisfies Cauchy-Riemann equations, and if at some point Cauchy-Riemann equations are not satisfied, then it is not differentiable. Okay. So let us do this problem now. Show that fz is analytic in a domain D if and only if f of z bar and f bar of z bar. So f is analytic if and only if f of z bar is analytic. You have the problem in front of you, so I am not writing in a domain D and all that. This is analytic. So let's do it. We know when f is analytic in terms of u and v. So let us write fz in terms of u and v. So let fz be uxy plus I times vxy. Remember f bar z is what? It is uxy minus I vxy. And what will be f bar of z bar? See, remember here z is x plus iy. So z bar is x minus iy. So if you change now the argument here, so f z bar, here it should be z bar, correct it. So f is analytic if and only if f bar of f z bar. Okay. Now what is f bar of z bar? Is, now this z bar means it is the imaginary part is minus y. So it is ux minus y minus I times v x minus y. See this. Have you understood this? That suppose f is uxy plus I vxy, then what is the dependence? This z is x plus iy, so that x and y appear here, and u and v are real and imaginary parts of f. So when we take f bar of z, z is same, therefore x plus x and y, but because of this f bar you will have uxy minus I vxy. Now when we change the argument to z bar, then in place of y, now minus y will appear. So f bar of z bar is this function. And we want to show that f is analytic if and only if f bar of z bar is analytic. Okay. Now, one thing is clear that u and v are differentiable if and only if u of x comma minus y and minus v of x comma minus y are differentiable. Okay. So, let us first write that, note that u, v are differentiable wherever in a domain, okay, in a certain domain, in a domain D, if and only if so u, if you change to minus y and minus v x minus y are differentiable. In D. So, real and imaginary parts of f are differentiable if and only if real and imaginary parts of f bar of z bar are differentiable. Now, our necessary and sufficient condition for differentiability of f is that the real and imaginary parts be differentiable and satisfy Cauchy-Riemann equations. So, what remains now is to check Cauchy-Riemann equations. That means if Cauchy-Riemann equations are satisfied by uv, then ux minus y and minus v x minus y also satisfy Cauchy-Riemann equations, and conversely we want to show that f is analytic if and only if f bar of z bar is analytic. So, suppose da by u by da by x. Okay, so suppose let us call this u x minus y as capital U x y. Suppose u of x y is small u x minus y and v of x y as minus v x minus y, because that is our new function f bar of z bar. Okay. So, now in terms of this capital U and capital V, we want to prove that uv satisfy Cauchy-Riemann equations if and only if capital U and capital V satisfy Cauchy-Riemann equations. F is uv, real and imaginary parts, and f bar of z bar is capital U and capital V. So, these two satisfy Cauchy-Riemann equations, small u, small v, if and only if capital V also satisfy Cauchy-Riemann equation. That is what we want to show now. So, what is da by u by da by x? Small u. Okay. Okay, let's capital U. Da by u by da by x. Now here, when you differentiate with respect to x, keeping y constant, whether it is y or minus y, it will be same. So, it will be da by u by da by x. What will be da by u by da by y? Capital da by u by da by y will be equal to da by u by da by y will be equal to what? This is capital U. Now this is replaced by minus y. So it is minus da by u by da, minus da by u by da by y. Da by v, in fact this is just change of coordinates. So you can first of all differentiate with respect to y, and this y is replaced by minus y. So derivative of y with respect to y is minus 1. Okay. Because this is just composition of other function, xy goes to x minus y. So you may apply chain rule if you want. So da by v by da by x. Now this will be minus, so this is small v, minus dabba V by dabba X and dabba V by dabba capital V by dabba Y will be, now minus minus will become plus, so small dabba V by dabba Y. Now look at these equations. Now we want to check whether dabba U by dabba X equal to dabba V by dabba Y. But dabba U capital by dabba X is this small. So if these two are equal, then these two are equal. So dabba U by dabba X equal to dabba V by dabba Y, if and only if dabba capital U by dabba X equal to dabba capital V by dabba Y. So if small u small v satisfy this equation, capital U capital V also satisfy. What about second equation? Dabba capital U by dabba Y equal to minus dabba capital V by dabba X, if and only if dabba V by dabba X is minus of dabba U by dabba Y. So if dabba U by dabba Y is minus dabba V by dabba X, then dabba capital U by dabba Y is minus dabba V by dabba X, because what is dabba U by dabba Y? It is minus of this. Okay. Now if that is equal to minus of this, then this will become plus, which is minus of dabba U by dabba Y. So is it clear that Cauchy-Riemann equations are satisfied? So UV, okay, so UV satisfy Cauchy-Riemann equations if and only if UV satisfy Cauchy-Riemann equations if and only if UV satisfy Cauchy-Riemann equations. Therefore, F is differentiable, F is analytic if and only if F bar, Z bar is analytic. That is, you may replace the real and imaginary parts u and b were u and minus v first, and then change the variable y to minus y. Then you again get analytic function. Okay. Now other thing that we want to do about Cauchy-Riemann equations is Cauchy-Riemann equations in polar coordinates. Okay. It is not written there, but you will get the revised notes where you will get the Cauchy-Riemann equations in the polar form. So you just pay attention here and don't have to write, because you will get the notes, though at present you don't see there. So let me write Cauchy-Riemann equations in polar coordinates. Cauchy-Riemann equations in polar coordinates. That means what? We know that a function can be written in the polar form. Okay. Just like you write a complex number z equal to x plus iy in the Cartesian form, and then you have corresponding real and imaginary parts of functions as uxy and vxy, which are also in terms of x and y. That is, u and v are also expressed in terms of x and y. So if you start with z expressed in the polar form, that is, suppose z is r cos theta plus I sin theta, then z itself is in r theta coordinates, that is polar coordinates. So uxy and vxy will get transferred into r theta coordinates. Then what are Cauchy-Riemann equations? Then what are Cauchy-Riemann equations for u and v in terms of the partial derivatives with respect to r and theta? So we want to find out Cauchy-Riemann equations in terms of r and theta. So let suppose z equal to x plus iy, this is Cartesian form, and fz to uxy plus I times vxy as usual. Now how do you get polar form of z? So the polar form of z is, z is equal to r cos theta plus I r sin theta. It's r into cos theta plus I sin theta. That is polar form. So that is, from Cartesian form we get polar form by substituting x equal to r cos theta and y is equal to r sin theta. Okay. So if x is r cos theta and y is r sin theta, then uxy can be expressed in terms of r theta. Okay. So by substitution, by the substitutions, x equal to r cos theta and y is equal to r sin theta, we get u and v in terms of r and theta. We get uv, in terms of r theta. Now can we find out derivative of u with respect to r? That means partial derivative of u with respect to r, can we find out? So what is dava u by dava r? Now I have not actually find out what is, you put here a r cos theta, r sin theta and so on, but you can apply chain rule. So that is actually dava u by dava x into dava x by dava r plus dava u by dava y into dava y by dava r. Have you done this? You have done this chain rule last time when you learned functions of several real variables. So this is only about the functions of real variables, nothing complex here. Okay, so this you have already done. Now let us keep this dava u by dava x as it is, and dava x by dava r we know because x is equal to r cos theta. X is equal to r cos theta, so dava x by dava r is cos theta. So this is dava u by dava x into cos theta plus dava u by dava y into dava y by dava r, but y is r sin theta. So dava y by dava r is sin theta. So this is sin theta. So this is dava u by dava r. Now what is dava u by dava theta? Dava u by dava theta is similarly dava u by dava x into dava x by dava theta plus dava u by dava y into dava y by dava theta. That is equal to, so dava u by dava theta is equal to dava u by dava x, and what is dava x by dava theta? Now again see, x is equal to r cos theta. So dava x by dava theta is minus r sin theta. So minus r sin theta plus dava u by dava y into dava y by dava theta is now r cos theta. I am just finding partial derivatives of this, x equal to r cos theta, y is equal to r sin theta with respect to r theta. So this is routine. Dava v by dava r is dava v by dava x into dava x by dava r plus delta V by delta Y into delta Y by delta R. Now delta V by delta X I will keep as it is. Delta X by delta R again is cos theta plus delta V by delta Y I will keep as it is, and delta Y by delta R is sin theta. So this is delta V by delta R, and delta V by delta theta is nothing but delta V by delta X into delta X by delta theta plus delta V by delta Y into delta Y by delta theta. That is equal to delta V by delta theta equal to delta V by delta X to delta X by delta theta. Delta X by delta theta is minus R sin theta. So minus sign here R sin theta, and plus delta V by delta Y into R cos theta. So this is expression for delta U by delta R. This is expression for delta U by delta theta, second equation. Then this is delta V by delta R, and this equation number 4 is delta V by delta theta. Now these equations number 1, 2, 3, 4, do you see equations number 1, 2, 3, 4? You see them again, maybe 1, 2, 3 and 4. Can you see simultaneously? Yes, camera. Can one see both all the 4 equations at a time? All right. So now suppose delta U by delta X equal to delta V by delta Y. So suppose U and V satisfy Cauchy-Riemann equations, and we start with Cartesian form. So suppose delta U by delta X is equal to delta V by delta Y, and delta U by delta Y is minus delta V by delta X. This is given to us, suppose. All right. So now see the first equation, okay, and delta U by delta R, if you multiply, okay, so delta U by delta R, if you multiply by R, see here, so if you multiply delta U by delta R by R, you get R cos theta here. If you multiply by R, you will get R cos theta here and R sin theta here. So you will get delta U by delta X R cos theta and delta U by delta Y R sin theta. But if you see this equation 4, then this is R cos theta delta V by delta Y, but delta U by delta X is delta V by delta Y. So this term matches, and then R sin theta is here minus R sin theta, but delta V by delta X is minus delta U by delta X. So this term also matches. So if you just multiply this R, multiply this first equation by R, you will get the fourth equation. So suppose this, then R delta U by delta R is equal to delta V by delta theta. So all the expressions delta U by delta R, delta V by delta R, da by u by da by theta, da by v by da by theta we have found. Now it is just this you multiply by r this side and observe that it is nothing but da by v by da by theta. Okay. Similarly, other equation, and the other equation that you get is da by u by da by theta is equal to minus r da by v by da by r, minus r da by v by da by r. Because if you see da by v by da by r here, equation number 3, and multiply by r, then it is r cos theta, r sin theta. And da by u by da by theta if you see, then it is this, it is minus, but this da by v by da by y is equal to da by u by da by x. Okay. So if you have minus r da by v by da by r, this minus r sin theta minus r sin theta, this term matches, and then minus r da by v by da by x is minus r cos theta, but da by u by da by y is minus da by v by da by x, so this term will match. So this equation is satisfied. So these are Cauchy-Riemann equations in the polar form. These are nothing but the Cauchy-Riemann equations in the polar form. Okay. R da by u by da by r is da by v by da by theta, and da by u by da by theta is minus r da by v by da by r. Okay. So let us use these Cauchy-Riemann equations once so that we will be more familiar with this Cauchy-Riemann equations in the polar form. So let us write some function. Of course, when I write polar form, it means that z is not equal to 0, of course. So z non-zero. Okay. So now consider function say 1 over r. So let fz equal to 1 over r, 1 over z. Okay. Now how can you write this? So suppose, so if z is equal to r into cos theta plus I sin theta, what is 1 over z? Then 1 over z is 1 over r, and you know that this raised to minus 1 is nothing but cos of theta minus I sin theta. So cos theta plus I sin theta raised to n is cos n theta plus I sin n theta, and this n you can take always an integer. So now this is cos minus theta, which is cos theta, sin of minus theta is minus sin theta. So this is suppose fz, so u in terms of r and theta is u r theta plus I times v r theta, which is nothing but here u r theta is nothing but what? 1 over r cos theta. So it is cos theta by r, and v r theta is nothing but minus sin theta by r. So u r theta is this and v r theta is this. Now you find out these partial derivatives. I will give you 2 minutes. Da by u by da by r, da by u by da by theta, da by v by da by theta, and da by v by da by r, where u is this, v is this. You have functions in terms of r theta. You find out their first order partial derivatives with respect to r and theta. 2 minutes. Your time starts now. You can start finding partial derivatives. Okay, so what is delta u by delta r? I wish I could hear you, but then anyways, delta u by delta r is delta u by delta r is minus cos theta upon r square, right? Minus 1 over r square cos theta. Delta u by delta theta minus sin theta by r. Delta v by delta r sin theta upon r square and delta v by delta theta minus cos theta upon r. Is this correct? Let us check. Delta u by delta r minus 1 over r square, derivative of 1 over r is minus 1 over r square cos theta. Delta u by delta theta, that means cos theta derivative is minus sin theta. Delta v by delta r, that means minus r sin theta up 1 over r square minus 1 over r, derivative is plus 1 over r square, and delta v by delta theta, derivative of minus sin theta is minus cos theta. So this is correct. Now let us check whether the Cauchy-Riemann equations hold. R delta u by delta r. What is R delta u by delta r? So this is delta u by delta r. You multiply by r. So therefore R delta u by delta r is equal to minus 1 over r cos theta. Minus 1 over r cos theta. See here, that is nothing but delta v by delta theta. So that is equal to delta v by delta theta. And what is second Cauchy-Riemann equation? Delta u by delta theta should be minus r delta v by delta r. So let us find minus r delta v by delta r. So we have already found delta v by delta r, that is this, multiply by minus r, so it is minus 1 over r sin theta, which is delta u by delta theta. This is what we wanted. So Cauchy-Riemann equations are satisfied. Equations are satisfied. And anyways, u and v are differentiable functions of r and theta. That's not a problem, because z is not 0. Of course, when we consider fz 1 over z, z is not equal to 0. So this 1 over r cos theta and minus 1 over r sin theta are differentiable functions of r and theta, being a rational function with denominator non-zero. So this is differentiable. Alright, and then this is trigonometric function 1 over r polynomial. And further they satisfy Cauchy-Riemann equations. So what happens? Corresponding function f is differentiable at all points. So this is differentiable at all points. Of course, at 0 I have not defined. So wherever it is defined, it is differentiable. So this is analytic in the punctured plane. Punctured means at 0 it is punctured in the sense that is omitted. So fz equal to 1 over z is analytic in C minus 0. And this we have verified by using Cauchy-Riemann equations in the polar form. So because Cauchy-Riemann equations in polar form are these, which we proved that they are satisfied, and u and v are differentiable functions. So by our theorem on necessary and sufficient condition for analyticity, we get that f is analytic. So this function is analytic everywhere except for 0. See, our stock of analytic functions is at present restricted. At present our stock of analytic function is restricted because we have not defined other functions like exponential functions, trigonometric functions, logarithmic functions, power, that is z to the power w, functions like that we have not yet defined. So we are just restricted by just saying that what are the examples of analytic functions. We have polynomial is the entire function, rational functions like this. So essentially polynomial and rational functions, that's all we can say. And what else you can do? Though we have not defined exponential function of complex variable, that is e to the power z, we have not defined. Sin z we have not defined. Cos z we have not defined. We are going to define these functions in the next chapter, maybe next week. But you may choose uxy and vxy cleverly, in the sense that, because there you can use real functions. You have already learned real functions, that is real exponential function, trigonometric function and so on. So you can use their combinations to construct u and v such that u, v are differentiable, and the cleverness will come into picture when you will have to adjust that the Cauchy-Riemann equations are satisfied. So that is one method of constructing analytic functions, but that is definitely not recommended, in the sense that how do you adjust u and v so that they will satisfy Cauchy-Riemann equations. So best thing would be to define these functions e to the power z, sin z, cos z, etc., and show that they are analytic, and that's how increase the stock of analytic functions. Okay. Before we go to the definitions of these functions, we will first finish some direct implications of analyticity in the domain. So again, let me repeat what domain means, which we did last time. Domain is open connected set. So domain is open and connected. And important examples are whole space, unit disk, z such that mod z less than 1, upper half plane, etc. Open and connected we want. Maybe punctured plane, this point deleted, okay, or you may delete finitely many points like this. This is also domain. Or maybe annulus, that is one circle, you have concentric circles. Annulus, that is also domain. And the important property of a domain, which we stated last time, and I told you that I won't give proof, because maybe proof you will do in topology course. But let me state that property again here, because that we are going to use in the next lecture today. That is the property of the domain. Let me show you in the notes. We saw that last time. Yes. Proposition 6.1, if you can see now on your screen, that in a domain D, any 2 points can be joined by a polygonal path, that is path consisting of finitely many line segments, and in such path the line segments can be chosen to be either horizontal or vertical. So if you have a domain like this, so suppose let's start with a nice domain. Okay, like this. This is suppose disk. This is open and connected. Now if I take 2 points, I can join by straight line and even one straight line. So such domains are convex sets. That means if you take any 2 points, I have a straight line which lies inside completely. I may take this point and this point. Okay? Any 2 points. Now if I go to this type of set, this is also domain, this is open, so these points I am considering. This is open, this is connected. Now if I take a point here and a point here, I cannot join by straight line. Okay. Given 2 points, there is a unique straight line passing through that. So that will not be completely contained in this set. So I cannot join by one line segment, but then I can always do like this. So these are points of the set. So these line segments lie completely inside. Okay. Not only this, I may choose line segment like this. This is horizontal line segment. This is a vertical line segment, and then this is horizontal line segment. So path consisting of horizontal and vertical line segments is possible. So for example, if you also take suppose annulus. If I take point here and point here, you cannot join by straight line, but you can join by something like this. Path consisting of horizontal and vertical line segments. So the property says that any 2 points of a domain can always be joined by a path, a polygonal path. That means a path consisting of finitely many line segments like this, say to start with. But then it so happens that we can always choose these line segments to be so that they are either horizontal or vertical. Horizontal and vertical means parallel to x-axis or parallel to y-axis. So once points are given, I can choose my line segments in such a way that the polygonal path consists of line segments which are parallel to the coordinate axes. So this theorem we want to use next time and prove some constancy results. That means under certain conditions, the function turns out to be constant. For example, we all know that with our experience of real variable, that is calculus, if the derivative is 0, then function is constant. So we want that property here also, that f dash is 0, then function is constant. So some other such results also hold, where we want to prove that the complex valued function of a complex variable turns out to be a constant function under certain conditions. But of course we are using the property of the domain of the definition of the function, that is the function is defined on an open connected set, And then this connectedness is crucially used. That means this is open as well as connected, and then any 2 points therefore can be joined by a polygonal path. And further we improve that statement by saying that the polygonal path can be so that it consists of horizontal and vertical line segments, so that we can use partial derivatives more easily. That's it. Okay. Otherwise also we can do, we can write the proofs, but the proofs become simple if we use horizontal or vertical line segments. So we'll see the proofs of this constancy statement